To wrap up chapter 1, we're going to look at mathematical reasoning. And there's two main types of reasoning that we talk about. The first one is inductive reasoning, and that's going to be the first blank here. With, inductive reasoning, you're going to take some very specific examples and try to make a general statement about them. So that statement that you're drawing, that conclusion that you're making, we call a generalization. With a generalization, it's a summary of your findings. It's not quite a proof. We'll talk more about that in a bit. It's not a proof, but it's a statement that you've drawn from what you have seen. The end goal is to then prove that generalization, and you have to be aware of what we call a counterexample. And a counterexample is something that can show something to be false. It disproves a statement. So if you have a generalization that you have found, but yet there is one counterexample, just one example to prove that it is not true, then that generalization is not true at all, okay? You cannot prove it. You cannot say this is good in all cases. It's just true in a few cases. So therefore, it's not a generalization. It doesn't work all the time. So that's what a counterexample does. Now, I've got the NCTM reasoning and proof standard here that you can read through. And I want to talk about how you could use this in an elementary school classroom. So we're going to talk about inductive reasoning, where we're looking for a pattern. And we're going to do this example here with numbers on a calculator. So you could do this even with students, and it wouldn't take very long for them even to see the pattern. If you multiply 1089 by 1 through 9 in order, you're going to start to see a pattern form. So 1 times 1089 is still 1089. Okay. When you take 2 times 1089, you get 2178. 3 times 1089 is 3267. You might start to see that pattern forming. 4 times 1089 is 4356. When you multiply by 5, you get 5445. Times 6, it's 6500, 34. Multiplying by 7, it's 7623. Times 8, 8712. And finally, when you multiply by 9, you get 9801. So hopefully, by maybe the third or fourth one, and you started to see there was a pattern happening. In the thousands place and in the hundreds place, each time the number was increasing by 1. So in the thousands place, we went 1, 2, 3, 4, and so on, up to 9. And in the hundreds place, started at 0, and then each time increased by 1 till you got to 8. In the tens place and the ones place, it worked the other way. It decreased by 1 each time. So in the tens place, it started at 8 and went down 7, 6, all the way to 0. And in the ones place, started at 9, and again, it went down by 1 to 1. So there is a pattern there. When you're doing inductive reasoning, you're starting out by looking at these patterns. Once you've seen a pattern, you can come up with a generalization. You're not proving it yet, so it's called a conjecture. And once you've proven that that conjecture is true, then it becomes a theorem. So in mathematics, if you're presented with a theorem, it has already been proven true. So we're going to look at one more example here where we're going to come up with a generalization. We're not going to prove it. We're just going to come up with a generalization. Before we get there, I've got the representation standard for grades 3 through 5 in here. This example that we're going to do, where we're going to come up with a generalization, you could easily do with 3rd, 4th, or 5th graders. I'm going to just draw dots to represent some trapezoidal numbers. So we've looked at triangular numbers before and pentagonal numbers. Now we're going to look at trapezoidal numbers. But in the classroom, you might want a manipulative, something physical for them to actually move around. But a trapezoidal number follows a very specific pattern. So the first one can be represented with 3 dots. So 1, 1, 1. So there's your first trapezoidal number. The second one, the second trapezoidal number, and you can see up here the representation with numbers. So you've got 1, then 2, 2, 2, and then a 1. So there's our second trapezoidal number. So you can see that trapezoid shape. Mine's not real perfect, but you get the idea. Then the third one is 1, then 2, and then 3 3s in the middle. The number in the middle is always going to be in 3. There's going to be 3 groups of this middle number. Then we work our way back down. So that's the third one. And so let me do the fourth. So the fourth one goes 1, 2, 3, and then there's going to be 3 4s here in the middle. And then we step back down. So I'm not going to draw the fifth one, but in the fifth one, you'd have 1 dot, 2 dots, 3 dots, 4 dots, then 5 dots, 5 dots, 5 dots in the middle. Then it would step back down, 4 dots, 3 dots, 2 dots, 1 dot. So that's how these are going to work. Now, if we count our dots, you'll see that in the first trapezoidal number, there's 3 dots. In the second trapezoidal number, if you just count 1, 2, 3, 4, 5, 6, 7, 8. Count in the third one, I'm not going to take the time to count these individually, but there's 15 of them. And in the fourth, there's 24. Now, down here it says, note that 1 plus 1 plus 1 is equal to 1 times 3. So 3 is 1 times 3. The second one, 8, is 2 times 4. The third one, 15, is 3 times 5. The fourth one, 24, that's 4 times 6. If I don't have it drawn, but if we were to do the fifth trapezoidal number, if you see this pattern here, okay, 1 times 3, 2 times 4, 3 times 5, 4 times 6, hopefully you can tell that the fifth one would be 5 times 7, or 35, okay? And we'll come back to that in just a second. But it says, show how the dots in a representation of a trapezoidal number can be rearranged into a rectangle with 2 more columns than rows. So I'm going to take the third trapezoidal number here as an example. In my notes on BlazeView, I show this with both the second, third, or with all 3 of the second, third, and fourth. I'm just going to do the third one here. But if I were to redraw that, so I've got 1 dot, then 2 dots, then the 3 3s in the middle, and then 2, then 1. And again, if you're in a classroom, your students would have manipulatives to really play with these. But it's not too hard to tell that you could take these 3 dots here on the left and bring them around to the other side. There's 1, 2, 3. And now you've got a rectangle, and it's a 3 by 5 rectangle. So that's where that comes from. You could keep going with this, but by this point, I think it's fairly easy to see what that pattern is. and it says using inductive reasoning, because we're not proving anything yet, we're just making a conjecture, just stating a generalization. What would the formula be for the nth trapezoidal number? So the first trapezoidal number is 1 times 3 dots. The second is 2 times 4 dots. The third is 3 times 5 dots. The fourth, 4 times 6 dots. The fifth, 5 times 7. So the nth would be n times n plus 2 dots. So that would be a conjecture, a generalization, not yet proven, but you're able to just see that by looking at these first few examples.